Welcome back. Today we're going to start our conversation on acids and bases. Understand that acids and bases are just particular types of substances that we want to focus in on because of their unique properties. Today we're going to start by talking about some of the differences between acids and bases, and then we're going to kind of build from there. Understand that when we're having these discussions, it might be a good idea to have your textbook somewhere close by, especially for today, because there might be a couple practice examples or something I pull from the text. So just keep it close. We might refer to it later. So let's talk about differences in acids and bases and either both physical or chemical properties. Now, taste is not something that you should ever be doing over in the lab area. You should not be ever putting anything in your mouth while you are working in the lab. But we do use acids and bases in a lot of other things like products that you might find at home or sometimes in food. So you can usually recognize if something is, has an acid in it or a base, depending on the taste. Acids have somewhat of a sour taste to them. So think things like lemons, right? Lemons have acidic juices in them. Other sorts of citrus also have acidic juices in them. Those are things that would taste like sour. Bases taste somewhat bitter. So anytime you've ever had a food that might have a bitter taste to it, it might be because it has a base in it, or maybe if you've ever accidentally gotten any sort of like cleaning product or soap in your mouth, that might be why you might recognize it as that bitter taste. That's because there's probably a base in it. The feel. So if you ever say, for example, again, this isn't something that you would want to do in a lab. You wouldn't want to like dip your hands in a strong acid or a strong base. But let's say you accidentally spill a little on the countertop and you get a little on your fingers. Acids are going to have like a water-like feel to them. Whereas bases, you absolutely can recognize when you spill the base because it has somewhat of a slippery feel, almost like soap. If you've ever had any sort of encounter in our lab area where maybe you get a little sodium hydroxide on your hands, you might feel that it has that kind of slick, slippery feel. That's because sodium hydroxide is a base. So acids react with metal, so we're going to say yes. And when they react with metal, they produce hydrogen gas. Do bases react with metal? No, they don't. The acid reaction is actually something you've already seen. If you remember when we did the molar volume lab where we reacted acid with, I think it was a magnesium strip, and we created H2 gas, that's the exact reaction that we did there. Electrical conductivity, they're both pretty good. We're going to say fair to excellent, meaning that some acids are pretty good at it and other acids are very good at it. Same thing with bases, fair to excellent. And we'll kind of get into that a little bit later as to why that is. Maybe you think about why that might be. So let's talk about indicators a little bit. An indicator, just as a definition, is something that changes color in the presence of a base or an acid. So I'm going to write that here. Changes color in the presence, I can't spell, presence of an acid or base. So these are things that we sometimes use to determine whether or not our solution has an acid or base in it because the indicator will change color. You might have heard about litmus paper or pH paper. Acids will turn litmus paper red, whereas bases will turn litmus paper blue. We have an indicator that we use constantly in chemistry. It's called phenolphthalein. That's how you say that word there. I know that it looks like just a collection of consonants, but it's phenolphthalein. Sometimes in my life, I've heard people pronounce it phenolphthalein, but that sounds kind of weird, so I've always heard it as phenolphthalein. So phenolphthalein is colorless in the presence of an acid, and it is a rosy, beautiful pink color in the presence of base. So those are some properties. Let's talk about how we can define acids and bases. We have three different definitions of acids and bases, and we're going to cover those periodically as we continue on, but let's just get them all out of the way first. So an acid is any substance that when it dissolves in water, it forms hydrogen ions. And those hydrogen ions could also, depending on what solution we're in, those hydrogen ions could also form what we call hydronium ions, which are H3O+. So that's called hydronium. So this is a Arrhenius definition of an acid. An Arrhenius definition of a base is that if we have some sort of base that's dissolved in water, it's going to produce hydroxide. That's going to be a Arrhenius base. I'll just give an example so you know what I'm talking about here. Let's say that I take something like hydrochloric acid and let's dissolve hydrochloric acid in water. Now when hydrochloric acid dissolves in water, this is kind of like what we've seen in the past where I'm going to write what's called an ionization equation here. It's very similar to a dissociation equation. When HCl breaks down into water, it produces H plus and it produces Cl minus. Because HCl produces that H plus, we would consider this an Arrhenius acid, meaning that's something considered an acid because it produces H plus in solution. Now, if let's say, for example, I have something like NaOH, which is what we were just talking about before, NaOH is going to break down into Na plus and OH minus. The OH minus that it produces makes it an Arrhenius base. So let's talk about Bronsted. Bronsted definitions of bases and acids have to do with the relationship between acids and bases when they react with each other. So a Bronsted acid says that it's a substance that donates a proton, and by a proton we mean H plus. In this situation, whenever we refer to protons, we're pretty much just talking about H plus. So an acid is something that donates an H plus to another substance, whereas a base is something that accepts an H plus from another substance. So again, just keep in mind that whenever we talk about protons, we're just talking about H plus. So take a second, let's grab our book. Let's look at this figure here, this figure 23.3 on page 576. I'll give you a second to get there. If you need a pause to get there, you go right ahead. But notice that we have the ammonia reacting with the water, and it's this nice big diagram that shows us how it works. And in this situation, the hydrogen on the water is donated to the ammonia. So then we have this ammonium, and then we have the hydroxide. So if you look down below, we have the chemical reaction that shows that there. So in this situation, the NH3 is accepting a proton. So which one is it going to be? Is that an acid or a base? Well, if it's accepting a proton, that makes it a base. And in this case, water is donating the proton, which makes it an acid. So the chemical reaction is shown under here. And notice there's this thing that's next to it that says conjugates. Well, I wonder what that means. Let's think about it a little bit. So let's look at the comparison between the base and the conjugate acid, so the NH3 and the NH4. What do you notice is the only difference between NH3 and NH4? You know, on a formulaic level, what's the only difference? Well, they're only different by about one hydrogen, right? So NH3 has 3 hydrogens, NH4 has 4 hydrogens. Now this is what's called a conjugate pair. And we're going to talk a little bit more about this officially as we keep going, but understand that conjugate pairs are only separated by one hydrogen. So the base always has a conjugate acid, and the acid always has a conjugate base. You can see that with water as well. H2O has 2 hydrogens, OH minus has 1. The acid has its conjugate base. And you can see this a little bit more on table 575. It has a list of bases and their conjugate acids. And you'll notice that the conjugate acids and the bases are only separated by one hydrogen. And you could flip this table. You could technically call it acids and its conjugate bases as well. It just depends on who's doing what. So let's do a little practice. On page 576, there's a little thing there that says identify the acid-base conjugate action. Let's just do problem number 2. Let's just do A and B. It says, so what's the conjugate base of each of the following? So those are acids. See if you can find out the conjugate base of each. Go ahead and give it a try. All right, I wanted to kind of walk you through the thought process here since we don't have a complete understanding of conjugates yet. Let's just kind of think this through. So we're looking for the conjugate base, which means that the thing we're starting with would be an acid. So when we're thinking about base pairs or conjugate pairs, we have two choices. We either can take in an electron or we can give up an electron. So in this situation, we're talking about the conjugate base, which means our original thing has to be an acid. Acids donate protons. So I drew the two different options that we have here. All right, the one on the left here for H3SO3+, that's if we accepted a proton, and the other one is if we donated one. So it doesn't make sense for us to accept a proton because we're not acting as a base right now. We're acting as an acid, so that's not the choice. This one has to be it. That would be the conjugate base. Same thing with H2CO3. It wouldn't make sense for us to accept a proton because it says that we're an acid and we are becoming a conjugate base, so then this goes away. And this is the thing that we're looking for. Let's do a couple more to kind of really drive home how this works. I'm going to show you one and then I want you to try one out on your own. But let's say that I have the reaction between CO3 minus 2 and H2O. And this is an equilibrium reaction, and we'll talk a little bit more about why later. And that's going to form HCO3 and OH minus. And what we can often do with these reactions is we can identify the acid and the base and its conjugate pair. So let's take a second, let's link things together. So what is the relationship between, or which one on both sides of the equation are similar? You know, which ones are only separated by one hydrogen? It's pretty easy to recognize. You might recognize that, well, H2O and OH minus are only separated by one hydrogen. And I also have CO3 and HCO. So let's think about who's doing what. CO3 minus 2, is it gaining an electron, or proton? Is it gaining a proton or is it losing a proton? From going from CO3 to HCO, I would say it's gaining a proton. So in this situation, it's acting as a base. But if we look in the reverse, is HCO3 gaining or losing? HCO3 is losing. So that means if one is acting as a base, the other one has to be acting as an acid. That's just how it works. It's a base and its conjugate acid pair. Now let's look at H2O. For every time I have a base on one side of the equation, the other thing must be an acid, right? One has to act as a base, the other one has to act as an acid. So therefore, water must be acting as an acid in this example, and that means OH minus must be its conjugate base. So that's the idea, and we can use that to identify each piece of this reaction. Go ahead and try it on your own. Let me write you up one. HSO3 minus plus HSO4 minus. And that's going to react to give us H2SO3 and SO4. Do the same thing that we just did. Kind of try and connect them and determine which one's the base and which one's the acid. Come on back when you're. So in this situation, hopefully you notice that the HSO3 is gaining an electron, so it's working as a base. Its conjugate pair on the other side is an acid. HSO4 is donating a proton, so it is acting as an acid. Its conjugate pair on the other side is a base. All right, so we have one more definition that we don't see as often, but it's still important to kind of keep in mind. It's called a Lewis definition of an acid and a base. Lewis looks at things based on electron pairs. So acids are electron pair acceptors and bases are electron pair donors. To behave as an acid according to a Lewis definition, the substance must have an empty valence orbital, and to behave as an as a base, they have to have a lone pair of electrons. I think that's supposed to say must, but it's a little goofed up. I think that's supposed to say the substance must have a lone pair of electrons. So let's look at an example. If we have BF3 and NH3, we're going to draw the Lewis structures. If you want to pause and draw the Lewis structures before me, you're welcome to do so. I'm going to draw them kind of close together so I can show this. These are my Lewis structures. I guess I'll put the lone pairs on here just to make sure I do a complete one. If we look at the Lewis structures and we think about each one of these things, right? So it says that in order for something to be an acid, it has to have an empty orbital. Well, if you think about BF3, it does have an empty sp hybridized orbital because it only goes to sp2. Ammonia has this lone pair, so it fills the criteria of acting as a base. And what it does is it's going to donate this lone pair to, the entire lone pair, to BF. So then we get a new complex that looks something like this. And we have the F's on here. And this bond here is often referred to as a coordinated covalent bond. So this is a coordinated covalent bond. And that's really all I really need to talk about. I mean, just make sure that you can recognize it and you can understand what the difference between a Lewis acid or base is, between a Bronsted acid or base. Bronsted acid bases donate hydrogens. Lewis acids or bases donate electron pairs. So it's really just more about recognizing the difference between the two. And again, I'm not going to get too much into the details here. That is what's again called a coordinated covalent bond. And we're actually going to kind of skip ahead a little bit, so you can skip through this section here and this section here, and let's pick up here at acid nomenclature. If we need to go back and talk about the other stuff, we can, but it's not really important right now. So let's just kind of get into nomenclature. We've named a lot of acids in this class, You probably have heard me say even at this point, hydrochloric, hydrofluoric, hydrobromic, but how are we naming those things? Like, what are the rules? That's what we're going to talk about here. There's two different types of acids. There's what called binary acids. These are acids that just have two elements, a hydrogen connected with a non-metal. And the way that this works is that we just have the way we say it is we say hydro, and then whatever the second stem is for the name. So hydrobromic acid, right? So an example of this would be something like HBr, which is something that you've heard us say before. Like I said, hydro and then bromic acid. Bromide being the second element, hydrobromic acid. What about something like HCl? That would be like hydrochloric acid. Or maybe something like HI, hydroiodic or hydroiodic. I guess it depends if you say iodine or iodine. I don't know. So hydroiodic acid. What about this one? H2S. This one's a little trickier. H2S, you might think that's hydrosulfic acid, but that doesn't sound good. So I think they just decided as a science community that we're just going to call it hydrosulfuric acid. Okay. And then, did I miss any? Oh, I guess I got one more. Don't want to forget old HF. HF is hydrofluoric acid. So keep those in mind. Just hydro-blank-ic acid. The other type is what's called a ternary acid. It's a little bit trickier. This is when we have three elements. We have hydrogen, oxygen, and some sort of thing along with it. It's usually an acid that's formed with a polyatomic ion. And if we have a polyatomic ion that ends with ATE, we have to replace the ATE and replace it with IC. A really easy way to remember this is, let's say that you eat an acid, say you're at home or something and you have like a very acidic thing. What does it taste like? Ick. So if I ate it, it's like ick, right? It's kind of silly, but it's a way to remember it. Ate, ick. And you replace the ate with IC. The other one doesn't have such a cutesy little thing to remember it. It's just ite and us or us. I don't know, however you want to say it. So you replace ITE with OUS. So let's look at a couple examples so you can see what I mean. What about HNO2? So HNO2, the NO2, if you think about it, nitrate is NO3, but NO2 would be nitrite. So how would I say this? I would say nitrous acid. And what about something like H2SO3? So SO3 minus 2 is sulfite. So this would be sulfurous acid. And then let's do a little more. How about HNO3? Well, that's nitrate, right? So if we were to place the nitrate, it would be nitric acid. What about, well, I'll give you some to try. How about that? How about you try these ones? H2SO4. How about you try H2CO3 and H3PO4? See if you can name those, and then come on back when you're done. Just do it for practice. So I got sulfuric acid because that comes from sulfate. I got carbonic acid because it comes from carbonate. And be careful here, this is a lot like sulfur. We don't want to just say phosphic acid. Phosphate comes from, it comes from phosphate. So this is phosphoric acid. Okay. There's also organic acids. We'll talk about that later. You don't have to worry about that right now. Let's talk about acid-base strength. I believe this is our last topic here. So just stick with me. I'm almost done. So let's talk about acid-base strength. We have two different types of acids and bases. We have what are considered strong acids or bases. These are acids or bases that completely ionize in water, which means they completely dissociate into their ions. And then we have a weak acid or base. These acids or bases only moderately ionize in water. So let's kind of draw really quickly like kind of a chemical reaction that shows the difference. Let's say, for example, I have HCl again. Before I drew just one arrow, it wasn't an equilibrium expression. That's because HCl is a strong acid and it dissociates completely into H plus and Cl minus. There's no more HCl left in solution. Whereas with a weak acid, there is equilibrium occurring here because some of it does not ionize and stays in solution. So say, for example, something like acetic acid. If acetic acid dissociates in water, it becomes H plus and CH3COOH. And it is an equilibrium equation. because it has both the acetic acid and the ions in solution, because it does not completely dissociate. So please understand that that's the key difference between the two. Now in class, I'm going to do a little demonstration for this, so leave this part blank. Stay tuned for more. We will add to this later. So let's talk about common strong acids and common strong bases. So the best way to remember the common strong acids and common strong bases is to memorize them. I wish there was a easier way to let you know that, but you have to just memorize them. So luckily there's not that many. The binary acids, the binary strong acids are going to be HCl, HBr, and HI. Now, we also have ternary strong acids, and that's when we have any oxo acid where the number of oxygen atoms in the compounds exceeds the number of hydrogen atoms by 2 or more. Some examples would be that we're going to really be focusing on in this class are things like H2SO4, HNO3, HClO3, and HClO4. So those are sulfuric acid, nitric acid, chloric acid, and perchloric acid. So please keep that in mind. Those are so as far as the acids, you have to memorize 7 of them. It's just really important that you take some time to memorize them. It's really, really important that you do because later when we start doing some equations or reactions with these things, they behave differently than weak acids or weak bases. So it's really important that you just have these kind of memorized. The bases are a little easier to keep in mind because any group 1 metal, notice that I said metal, meaning I do not mean hydrogen. Any group 1 metal bound with hydroxide is considered a strong base. So I'm talking lithium hydroxide, sodium hydroxide, potassium hydroxide, etc., etc. Those are all considered strong bases. The other groups are from the second group metals, but it's not all of them, it's only the heavier ones. So calcium hydroxide, barium hydroxide, and strontium hydroxide are all considered strong bases. Again, you got to memorize these, but I think the bases are a little easier to remember than the acids. Anything else? If it's not said that it's a strong base or a strong acid, sometimes even if it's not on this list, a problem will just say something is strong. In any other situation, you have to assume that the acid or base is weak, and that has big implications. So the weak acids and weak bases, as we said before, these are only going to moderately ionize, and they will not dissociate completely. So they have an equilibrium equation going on. And equations for these should always be shown as equilibrium equations. So it's really important that you know which ones are strong, which ones are weak, because we even write the equations differently. Let's say, for example, if we're looking at HNO2, so this is not one of our strong bases. Let's just say that we have HNO2 reacting with water. When we write the equation for this, we're going to have H3O plus and NO2 minus. So in this situation, we know that HNO2 is acting as the acid because it is a stronger acid than water, at least. So it's going to donate its proton to water and then become a base itself. Let's look at another one. What about NH3 and H2O? Why don't you take a second and pause and see if you can write what the products are. So you know that NH3 is not an acid because it doesn't have an H in front of it, right? Acids always at least have an H in front of them. So it must be acting as a base. See if you can write the products to figure out what the products of this base reaction would be. Now, something to keep in mind is that NH3 is a weak base. And with other weak or strong things, so say for like weak acids, or strong bases, we don't always have to include water in the reaction. But for NH3 or any other weak base, if we're going to draw the ionization equation, it has to have water. You might ask yourself, well, why is that? Well, because the proton has to come from somewhere. You probably recognize when you were writing this yourself that NH3 gained a proton from H2O because H2O is acting as an acid. So let's actually take another second and let's do like we did before when we identified conjugate pairs, and let's do that for these two examples here. So take a second and do some connections just to show you what I'm talking about. For example, like HNO2 and NO2 are conjugate pairs. Do that for the rest of them. Like for all 4 different things involved in these 2 reactions. Go ahead and give it a try, and then come on back when you're finished. All right, so hopefully this is what you did. And this is a nice little segue here because you might notice that between these 2 reactions, water is acting as both an acid and as a base. Well, this is what's called an amphoteric or amphoteric substance. If I have a substance that can act as both an acid or a base, depending on the scenario, that is what's called amphoteric or amphiprotic. And remember, we kind of already talked about this, so let's do it officially in the notes. If I have something where I have a difference only of 1 proton between 2 substances, that's what's referred to as a conjugate pair. So if we're looking at the examples that we just talked about before, we already did it, but the conjugate pairing between those 2 things, that's what a conjugate pair is. So let's do a little more practice, just so we can understand how this works. I mean, this is, like I said, the official moment where we talk about this in the notes. Let's write the balanced equation between HF and ammonia. And then we're going to identify the conjugate acid pairs. You do that first, and then come on back and I'll show you how to do the second part. So notice that HF is a weak acid, NH3 is a weak base. So HF is going to donate its proton to NH3. So we get NH4 plus and F minus. And if we connect them into their conjugate pairings, HF and F minus are pairs, NH3 and NH4 are pairs. And I've just been abbreviating A for acid, B for base. I'm kind of doing it a little quickly. Now, how do we know this reaction goes one way or the other? Like, why isn't it that HF isn't because we have, if you think about it, let me kind of rephrase what I'm saying. We have 2 acids in solution right now, right? We have HF as an acid, and we have NH4 as an acid. So how do we know which one's stronger or weaker? Well, we know that HF is a weak acid, but we know that it is a stronger acid than NH4. So how can we figure out which side of this equation is going to be happening more often? Well, in order to determine that, we have to think about what it means for something to be an acid or a base. In order for something to be an acid, it means that it is a proton donor. So in other words, who's the biggest loser? Is HF going to completely give up its hydrogens more than NH4? Yeah, probably. So HF is going to give up its hydrogens more than NH4 is, which means that our reaction is going to favor the products. So we favor the products. We shift to the product side. So that means the forward reaction has a higher rate than the reverse because HF is more likely to donate than NH4 is. So let's look at one more example and then we'll be done. What happens if we have HClO3, HClO, excuse me, not HClO3, HClO and ammonia. So go ahead and give this one a try from the top and come on back when you're finished. Let me erase this so you can try this one out as well. Come on back when you're finished and we'll talk it through. All right, so this is what we got. We have HClO, of course, is acting as the acid. NH3 is acting as the base. In this situation, it says NH3 is a stronger base than ClO minus. So which side is favored at equilibrium? Again, it would be the products because NH3 is going to be quicker to accept. It is a bigger proton acceptor than ClO minus. So it will push the reaction to the right. So it's going to favor products. A good rule of thumb is just that our reaction is always going to shift away from the stronger thing. So if the question says this is a stronger base, which way do I go? You always shift away from the stronger side. And that's it. That's all. I know that this was kind of a lot, so I really appreciate you sticking in there. And we will see you next time.